Okay.
So let's start again with Jorge. First, just a friendly reminder, as yesterday we can meet at Universe Flat around 8 for going to dinner. Whoever wants to come is. And I don't know the adjective. So the next speaker is Jorge Noreña, and I hope I pronounce it well.
Yes. Actually, it's one of the better Italian pronunciations of my name that I've heard. So I'm going to be a little bit science fiction in the sense that imagine that someone actually manages to measure the galaxy bispectrum, and I maybe I'm one of the few, but I really think that the most interesting thing that we can do with galaxy surveys is constrained fundamental physics such as neutrino properties and primordial non-Gaussianity. I'm of the camp that dark energy is lambda and that's it. So that's why I want to focus on this. That's why I want to focus on the bispectrum. First I'll give you a very brief introduction of sort of as a motivation of why I'm doing this. That seems a bit like a complicated calculation, so it has to be well motivated. Then I'll talk a bit like about the status of the subfield. So what people have done for the relativistic galaxy power spectrum and bispectrum. I'm going to miss one recent, probably relevant paper that I haven't had time to read, and since this talk was short notice, I didn't have to read it before today. Which is a recent paper by Enea Didio and Uroš Seljac that compute the one-loop galaxy power spectrum with relativistic effects. And finally, I'm going to tell you about the first steps towards computing the relativistic galaxy bispectrum. So first motivation. So non-Gaussianity is basically higher-order correlation functions, and so we want to look for this primordial three-point function that, due to translational and rotational invariance, you can write in this way, and theorists call this the bispectrum, this B here. I know that in astrophysics, the bispectrum is the Fourier space thing, and the three-point function is the position space object, but for theorists, the two things are exchangeable, the two terms. So forgive me if I say three-point function when I mean bispectrum or vice versa, because that's how I was brought up, even if I know the difference. So I will always be talking about Fourier space. So if I say three-point function, you should think bispectrum. And you can plot the bispectrum if you assume scale invariance, you can plot it in this parameter space. And then you have the famous configuration. So the three momenta have to form a closed triangle due to this Dirac delta, and these are the famous configurations, the equilateral one around here, flattened one around here, and squeezed one around here. And I really think that it will be extremely difficult to measure or to improve on Planck constraints for equilateral configurations, because it's the type of non-Gaussianity that is also induced by gravitational non-linearities and nonlinear biasing that will be there. So it will be difficult. I'm not saying it's impossible. It will be extremely difficult. But there is some hope, some vague hope of improving the constraints on the squeeze limit, because the squeeze limit is more robust. You cannot produce a squeeze limit simply with astrophysics. And I can give you a more detailed argument, but I want to talk about something else. And we are lucky because the squeeze limit is also one of the most interesting things theoretically to look for, because the squeeze limit has information about the field content during inflation. And we know in a series of papers that we know that if inflation is single field, the bispectrum should behave like this in the squeeze limit. So if you mass spectrum for your fields, you have a bunch of very massive fields that you can ignore. because they are too massive, much more massive than the whole scale, and only one field, the inflaton, which is much lighter than the whole scale, then the bispectrum, the primordial bispectrum, has to have this behavior in this limit. And we also know from explicit calculations that multi-field models, if you have several light fields, can produce a bispectrum that goes like this. So it has a stronger divergence in the squeeze limit. And notice that there is 2 powers of Q, 2 powers of the momentum going to 0, more here with respect to the single field case. So this 1 over k, this is the famous 1 over k squared or 1 over q squared that you always hear about when people talk about local non-Gaussianity. And you can even have intermediate behaviors if the fields have masses close to h. So you can even interpolate between these two. And there are some claims that if you get higher powers, it's not even inflation. And I stole this figure from this paper here, just because I like it. And there are also more recent claims that tell you that you could even try to measure the spin of these extra fields, claims by Cora Dvorkin, who I think is no longer in the audience, and Asadeh Moradinejad, who study models by other people, Arkani Hamed and Bauman, Maldacena, and others. So my motivation is this. I think it's very interesting to look for the squeeze limit, and it's also very robust against astrophysics, so we are lucky. And so we should really look for the squeeze limit of the bispectrum. And the main observables that you can use to constrain the squeeze limit of the bispectrum is to try to improve on Planck are either the galaxy bispectrum itself, about which I will tell you more later on, or the galaxy power spectrum, because the presence of a local type non-Gaussianity induces a 1 over k squared behavior on the galaxy bias, on the linear galaxy bias. I can tell you more why. I just don't have time, but I have some slides prepared for that. So if someone wants to ask, don't be afraid, and I'll tell you why that happens in the galaxy power spectrum. And so this 1 over k squared behavior can also be induced simply from relativistic corrections. And that's very simple because so physically you cannot have this behavior cannot be induced, but meaning that if you are standing on a galaxy, you will never be, so this 1 over k squared is a correlation between the gravitational potential and the, say, galaxy number per density. And if you use Poisson's equation, then you notice that times the galaxy power spectrum, right? So this is the famous 1 over k squared. This type of correlation cannot, it would mean that you can measure the local gravitational potential. Of course, you cannot. It's not physical in some sense, but it can appear due to projection effects, due to the fact that you are not standing on that galaxy when you measure things. You are standing here, and you have to consider the propagation of photons to you. So let's look at some of these effects for the galaxy power spectrum. Some of the effects that can induce this type of correlation on the observed galaxy power spectrum. So let's define the galaxy number over density in this way, where the average number of galaxies is given by this. The number of galaxies, the total average number of galaxies divided by the volume. And the kind of things that can happen are, well, your observed redshift, as you know very well, is not the real redshift of the galaxy, because things like peculiar velocities, as you know very well, can distort this redshift, and that's the sort of Newtonian contribution. But on top of that, you can have higher order relativistic contributions. But also the angular position of the galaxy can be modified due to lensing. Today we heard a lot about that. But there are other relativistic effects that I didn't write, are in these dots, that can also modify this position. So you modify both the redshift and the position, and they both contain relativistic effects, and they affect your measured galaxy contrast. And moreover, these effects induce sort of additional biases that I'll tell you a bit more about, and we should worry about measuring these biases if we want to measure primordial non-Gaussianity. And there is hope to measure them and really disentangle them. And the additional biases are these two. The first one is that, well, the distortion in redshift affects the average number density. So you really have to worry. So this number will change, and you can interpret it as a contribution to this when you change the redshift. And this thing will be proportional to the so-called evolution bias, which is the derivative of the number of galaxies with respect to redshift. That's called the evolution bias. And it is completely degenerate with local FNL in the scale-dependent bias, as I will show in a plot. Another effect is that another important effect is that the coordinate volume is different from the physical volume. So also that will change, and it will also induce an effect that can be degenerate with local FNL, but it's perfectly computable. And finally, lensing magnification makes galaxies appear fainter or brighter. So if a galaxy is at the threshold of being observed, lensing magnification can bring it into your survey or out of your survey, and this can also change your number of your measured number of galaxies, and this is parameterized by something called magnification bias. And everything I'm saying here was already done like 8 years ago by these groups, or 7 years ago by these groups. And the result is this. They get an effective FNL that depends on redshift. And this is for different, this Q here is the same T, is connected to the T that I said before, to the evolution bias, the magnification bias. And you see that you can, and this is something that depends purely on the astrophysics, because it depends purely on the luminosity of the galaxies of your sample. So it's not something you can compute, you really have to measure it on your sample. And it can induce some fake FNL of order 1. That's the conclusion, which is what you would like to measure if you want to improve over a Planck. You want to go for FNL of order 1. Okay, very good. And I took this plot from this paper here. Very good. So that's, and there is the more recent paper by Seljak and Dio that I haven't had time to read. So also go to that one. But now I'm going to move to the bispectrum. So now we want to so another observable that you could try to measure is the relativistic bispectrum. This has some advantages. For example, if you are interested in these higher spin fields, that signal would be washed out in the power spectrum. There will be a little bit of signal, but not enough to be useful. So you would really want to go for the bispectrum. And that's just an example of the usefulness of the bispectrum. And so how would you go on, how would you compute the relativistic bispectrum? So the first step is that you expand the metric and the stress tensor to second order in perturbations. So you have to fluctuate, you take a perturbed Friedman-Robertson-Walker and you compute. The second step is you fix a gauge, and there are several popular gauges. One of them is the Poisson gauge, which many people are familiar with, or the synchronous gauge, which is defined by the fact that your coordinate time is the proper time of each observable. So that's your gauge condition. And it is believed, I mean, there are arguments to say that this gauge is more useful for describing biasing. So you fix a gauge. And the third step is that you take everything, all the fluctuations to be small, and you simply solve your Einstein and fluid equations to second order. So that's what you do. And to finish, you have to solve for the photon geodesic at second order to get lensing and redshift space distortions. Plus, their relativistic counterparts and generalizations. And a lot of people have been working on doing this. So here are the papers by 3 different groups. And I didn't cite all of them because it's really a long list. So people are trying to do this because it will be degenerate with FNL of order 1. And I did this also some years ago in some approximation. So we were simply looking for a correlation between phi, a long wavelength gravitational potential, and a short wavelength galaxy over density. And this was the result. But we used some tricks. I don't want to describe it. I just want to say that we again get FNL of order 1. But this has the problem that the long wavelength gravitational potential has to be super horizon. So it's not very useful in practice. Now, all these studies have a limitation, that they have all been done to leading order in perturbation theory. And that means that they break down at small scales. Now, you may say that everything is fine because relativity is important only at large scales. And at small scales, it's basically Newtonian. And that's true, except for the fact that the bispectrum couples scales. And except for the fact that I'm interested precisely in the squeeze limit. So when one of the scales is very large, coupled to a very short scale. So I'm interested in the regime. The interesting regime is precisely the regime in which you are both nonlinear, because the short scale is nonlinear, and relativistic, because the long scale is relativistic. So these previous studies are not enough for that. And let me be more precise on this. I can be more precise on this. So let's estimate how big these effects can be. So let's imagine that your observable overdensity, I can expand it like this, just parametrically, just to estimate how big these things are. So some linear overdensity, some quadratic kernel, and then relativistic corrections of this type that, well, some first order and some second order relativistic correction. Like so nonlinear relativity and linear relativity. And I put that in a bispectrum. So I get a correction due to this linear term that goes like this, and a correction due to the nonlinear term that goes like this. And we notice that parametrically, they are of the same order. So you have to compute the second order relativistic corrections. That's trivial. I mean, you know that the bispectrum at 3 level, you have to go to second order. Let's see what happens at one loop. So at one loop, there are several contributions from the third order kernel and the fourth order kernel and so on. Let's look at the third order kernel for simplicity. So we have a Newtonian third order kernel and a relativistic third order kernel that again has this type of correlation. And so this is the Newtonian contribution. Only one of the contributions to the one loop bispectrum. And this is the relativistic contribution. And where this is coming from here. And we see first that there is no parametric suppression. It's only the loop suppression that makes this term smaller than this one. But if you are going to scales where, say, k of 0.1 or something, so if you want your short scales to be nonlinear, you have to consider the one loop corrections. So then the one loop suppression in this term in principle disappears. There's no a priori suppression. So it seems that if we want to compute the relativistic contamination to the galaxy bispectrum in the squeeze limit, which is, in my opinion, in my very biased opinion, the most interesting regime, then you should do a nonlinear relativistic calculation. Now, of course, and then you would have to go to fourth order because you need to keep up to F4 in the one loop bispectrum. Now, of course, that seems almost impossible. I mean, in GR, if you open these papers of the groups that I showed, equations are 1 page long. So, and they are only at second order. So a priori, it looks like an insurmountable task. But we are saved by the following fact. We are only interested in the leading relativistic corrections. They give FNL of order 1. So they are corrections of the order of 10 to the minus 5. FNL of order 1 means 10 to the minus 5. So subleading corrections will be suppressed by additional powers of 10 to the minus 3 at least. So let's forget about that. Those are completely useless. And let's focus only on the leading relativistic corrections. And notice the following, that even here, even on Earth, the gravitational potential is very small. It's of the order of 10 to the minus 5. So even when you go to a very nonlinear structure, even like Earth, the gravitational potential is always very suppressed. And velocities are always 10 to the minus 3. Otherwise, we would have discovered relativity hundreds of years earlier. So even in very nonlinear objects, velocities and gravitational potentials are suppressed. Density, however, becomes nonlinear, as you know very well. So let's make an example. This is simply as an estimate. AH is the horizon, is order 1000 megaparsecs. And let me take k of 0.1, and then easily this thing becomes of order 1. If you plug here 10 to the minus 4, this thing easily becomes of order 1. So that's why delta becomes order 1, even if phi is 10 to the minus 5. So that's why gravity is, even Newtonian gravity is nonlinear, as you know very well. Okay? So now we can write equations which are fully nonlinear in delta, but perturbative in this, using the so-called weak field approximation. In other words, we take derivatives to be large, and then you can write the equations, because Einstein's equations have a finite number of derivatives. So you can write the fully nonlinear equations in the weak field approximation and simply solve. In the end, I mean, you get some relativistic nonlinear kernels. I didn't write, they are longish, but they are not 1 page long, only like 3 lines. I didn't write them. And of course, you get the usual Newtonian nonlinearities. And so these relativistic nonlinearities that are suppressed by this, which is my relativistic approximation, how much you are inside the horizon for the long mode. So this will induce a relativistic correction to the kernel that parametrically has to go like 2 powers of the horizon because it has 2 powers less of derivatives. Okay, so we computed these relativistic kernels. We computed the relativistic kernels. I will show you the result first, and then I will go to some more technical details if I have time. So the result is the following. We did it in both popular gauges, the synchronous and the Poisson gauge. And let me just emphasize before I forget, because I forgot to write it in the paper that you find on the archive, that to emphasize it enough, that this calculation, of course, doesn't give anything observable because we are computing correlation functions for the density contrast, which is not what you observe, of course. And that's even a gauge-dependent quantity. So what we actually computed is the 4th order metric in this approximation. And then in a follow-up, we will look at actual observables. But just to see whether the intuition that these effects are important is correct, let's take the bispectrum for this density, which is gauge-dependent. And this is what we do here. We compute the bispectrum as you take the squeeze limit. Right? So here it's equilateral, here it's squeezed, where one of the scales has been fixed to be nonlinear, so 0.1. And this is for the synchronous gauge, this is for the Poisson gauge. The blue line is the 3-level Newtonian bispectrum. The green line is the Newtonian 1-loop bispectrum. The purple line is the effect, is what you would observe if you had FNL 1, FNL equals 1. And if you believe claims in the literature, you will be able to observe this purple line in some sense. The red and the orange are the relativistic corrections. The orange line is the 3-level relativistic correction, and you see that it's very degenerate. The shape is is the same as the primordial signal, and the red line is the one-loop correction, which again gives FNL of order 1. Moreover, the relativistic one-loop correction, as you get close to the horizon, becomes as important as the Newtonian one-loop correction. For the one that is going to the horizon is the long wavelength scale. Remember that for spectra there are always 2 scales, not only 1 scale. So 1 scale is always nonlinear. That's why loops are so big. In the Poisson gauge, we get even that the one-loop result is bigger than the 3-level result, the relativistic 3-level result. That doesn't mean that perturbation theory broke down, because you should compare the one loop to the total 3-level, and it's still smaller than the total 3-level. It becomes bigger than the total 3-level at very large scales. So it tells you that, and in principle, I don't know the actual observable quantity, if it will be similar to this one or this one. There is no parametric argument. So it really has to be computed, which we will do in next year, right? So that's it. I think I don't have time for the technical points. So we computed, I put it in red, the metric to 4th order. And the relativistic effects can be important for the measurement of primordial non-Gaussianity in the squeeze limit from galaxy ray spectrum, but also power spectrum. Okay, that's it.
We have time for some question before the wrap up.
So your last 2 plots, you had this gauge-dependent result.
Yeah.
I'm sort of struggling to figure out what that means. So what is the relevant gauge-independent observable that you would then put this
again,
into?
This is what we are computing now. I still don't know. This gauge-dependent simply because the density, the dark matter over density, is a gauge-dependent quantity.
Sure.
So, of course, if you compute the 3-point function of dark matter over density, which is what I'm plotting here, you get a gauge-dependent result. But the gauge-independent object would be the galaxy number, the observed galaxy number over density. It would be an object that you observe on Earth after propagating the photons from the galaxies until your telescope. That's the gauge-independent quantity that we are computing.
Okay, so
this is only to show that, in principle, these one-loop effects can be important.
But that's a gauge-dependent statement. So it might work out that they are super important.
So I'm saying
until you have the gauge-independent observable, you can't be sure about that.
No, sure. But there is no argument to say that they are small. That's the point.
Yeah. Okay. All right.
Yes. So if you do an order of magnitude estimate, you get this, and then you get that they are important.
Okay.
And the first step to computing that is computing the metric, which is what we did. Yeah.
So I guess I'm just wondering how different is this population from the trick that you mentioned of just using the diff invariance to generate 4th order solution? Because I guess that you're always calculating things with 1 phi and in the squeeze limit.
Yes.
So can you generate this metric?
Yeah, the problem is that it's difficult to generate that. So that's what I did with Tony Riotto and Asadeh Moraniyajad and in 2015. But that's rigorously only valid when the long mode is super horizon, right? Oh. Because as soon as it becomes sub-horizon, curvature effects start becoming important. So then you don't know. I mean, you can guesstimate, but.
I see. So it is not only important that there is separation of scales. It is also important the horizon plays some role.
There has to be separation of scales, but also you have to have that Q better than the one over the horizon, right? Much smaller. Yeah, Q has to be much smaller than also AH.
Thanks.
Right.
Okay, if there are...
You said you just consider dark energy as lambda, but would you have an idea how would that change in quintessence models where perturbations can be important on very large scales?
So that's a good question. I actually don't know much about whether the bispectrum will help with dark energy observations. I remember a paper by Licha Verde and others some years ago that was claiming that it didn't help much for Hornensky models, but I never read the paper, so I don't know what my opinion on that is. For sure, the squeeze limit, it's very difficult to write a model that modifies the squeeze limit of the bispectrum. You have to violate a model that induces a signal that is the same as the primordial signal, you would need to violate something like the equivalence principle. And it's actually very difficult to violate the equivalence principle in a meaningful way. So yeah, maybe if you have some crazy model that violates the equivalence principle, maybe it will induce also this kind of behavior in the bispectrum. This 1 over k squared, which is what is plotted here in purple. But it's not easy. I mean, it's a bit exotic. But your usual quintessence, Hornensky, blah, 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 they don't induce this signal. Yeah.
Okay, let's thank again Jorge. If the speakers of today can please come here in front, we can start the wrap-up session. Thank you. Then, let's start with the questions.
To cluster people. So Massimo showed some measurements of velocity dispersions in galaxies. Can you use that to assess the mass of the cluster? How difficult is that for cosmological catalog? Of course, you need spectroscopy there, but can you do something to try to improve the scaling relations?
Well, the answer is yes. The short answer is yes. Problem is that it's a quite complicated task to measure velocity dispersions for so many galaxies that you might need to measure a mass profile, but definitely it's something that you can do. Indeed, in the framework of the Clash collaboration, where it was possible to combine where it was possible to combine lensing measurements with also measurement of velocity dispersions of galaxies in 13 of the cluster fields of the Clash fields. We made a comparison between the different mass estimates, so we could assess what are the kind of differences in systematics that affect the two measurements. Typically found quite good agreement between the mass profile derived from dynamical measurements and what was derived from lensing. Of course, you should expect some difference in the sense that some particular objects, those that are maybe mostly perturbed and out of equilibrium, they could have biased measurements when you use this kind of technique to measure the mass profiles.
So I guess it's one of the things that Mariana mentioned. So I don't know if, right. So scaling relations in particular, for example, TSZ is connected to physical quantities, you know, like pressure and whatever. In principle, you marginalize over all of the scaling relation parameters because you don't care about it, but maybe you could learn physics out of them. So I wonder, and I guess the answer is yes, but I don't know, if there's a way of quantifying this. But a thing that you could do is measure those scaling relations, look at a hydrodynamical simulation, see what you need to tweak in a hydrodynamical simulation to match those scaling relations, and then see how that affects whatever uncertainties on your power spectrum or something like that. So I don't know if anyone has thought about use.
If I understand, to calibrate, to check these meso-observable relations in simulations.
Yeah.
And then bring back to, is that right?
Yeah.
Actually, I think that for simulations, anybody simulations, when you talk about cluster cosmology, you have just anybody simulations for halos. You cannot, we cannot simulate a large number of clusters giving all observational properties that you expect in real data. So I don't think for now we are able to do something like this because our simulations are not close enough to real data. But once you can simulate I don't know, maybe for richness, I don't know if we can already do this for simulations when we paint some galaxies and you can try to infer the richness. Maybe for richness you can do this, but SSE, X-ray, and even with cleansing, I don't know if we are already able to do this. First with simulations. I don't know if you have more.
I'll just add a little bit on which is that, you know, you can paint galaxies in the sims, but it's just a matter of you kind of have to pick and choose what you get right? So like you can get the red sequence right, but you might not get all galaxy clusters right, or you.
What the TSS signals would be, and then you can see whether that mass observable relation matches the one that you see in calibrated cluster count in real data, and then use that to inform your solution. I just don't know if that's any use at all. I don't know whether that.
Well, certainly it could be used as a good consistency check, right? Like making sure that if you put things in, you get those same things out again when you do your constraints. Yeah, I think one area where it can definitely help you, even in sims where you know what you're putting in, is constraining correlations between observables, right? So like understand it, like you can put constraints on the the correlation between a TSD signal and a richness or something like that, and that can end up helping you later down the road. Or at least it can tell you what it would take to make good constraints. So some forecasting can be done with that.
Just to add a last point, like I think the major issue now is the computing power. Like having a hydrosim at a cosmological scale is pretty unacceptable. Just to give you an idea, I think we looked at, say, Illustris or something. The number of clusters that we can use for like things like Red Mapper was a handful. So it's like we're still quite a long ways off from being able to cosmologically simulate that. And the second point I want to add is eventually it might come to a point where you're just asking, it's kind of circular, right? Whether the physics you put in the sims were correct. So we've done a lot of tests on RedMapper, but then it ultimately comes to whether the colors in RedMapper was correct in order to have RedMapper run. So it's all asking the same question, whether we understand the physics, but it might ultimately come out to that in the end.
So I have a question for, I think, also the cluster and weak lensing people. So I was wondering if in the case that you try to measure masses with weak lensing, for example, and I was talking to Tom, and you use, for example, the amplitude of the clustering on the true halo term. That's basically something that depends on the bias that you assume. And it's sort of seen in simulations, I mean, it's clearly seen in simulations that the clustering depends on other parameters in addition to mass, right? It's a smaller dependence. But seeing, for example, I don't know, like the slightly offset values that you get for sigma 8, I was wondering, maybe is there some, I don't know, influence from assembly bias? Is there a way to marginalize over it, or is it taken into account in some way?
Yeah, that's a good question. So if anyone didn't hear, the question was, you know, is there, if the two halo term depends on the halo bias, do you have to worry about assembly bias at all? And at this stage, we don't worry about it, because if you're confident that your selection function is well understood, then you know what masses are included in your, or you know how that matches up to mass, right? Like if you don't think, or put it another way, if you don't think that richness correlates with things that influence assembly bias, then you don't need to worry about it. And I think the answer to that is probably not.
So can I make just a follow-up question? So maybe I lost the explanation of this, but what is, do you think is the reason for the slight difference in the sigma 8? Oh, sorry, I'm not using this properly. Apparently, yes. So I was wondering if the offset in sigma 8 is something that you guys are understanding where it's probably coming from. Maybe you explained this before.
I'm not sure I follow the question.
When you obtain, I think it was in your talk, the sigma 8 versus omega regions of high likelihood, they seem to be offset from the typical values that people find, right?
Oh, where the simulations were?
Yeah.
I'm still not sure I understand the question.
Oh, that's okay.
Okay. If you ask me after, then I'll definitely think about it more.
Okay.
So I have a question for Jorge. I always get confused about this gauge invariance or gauge variance, gauge dependence. So if I'm computing the power spectrum from CAMB, for instance, it uses a gauge, synchronous gauge. So is the power spectrum that comes out from CAMB gauge dependent or independent?
So it's yeah, CAMB computes the power spectrum of density, dark matter density, so it is gauge dependent. You cannot, I mean, you can use it at small scales where Newton holds and all the gauges should give the same Newtonian limit. But large scales, it will be gauge dependent and it has no relation to an observable. So you can use it to plug it into some more complete calculation where you propagate the photons of the galaxies until the telescope, etc., etc., etc. And then you get a gauge-independent quantity because it will be something that you actually observe. Yeah, but in principle, it's sorry. No, because you haven't worried about relativistic effects, right? So you've never worried about these very large scales close to the horizon. If you do, then, I mean, I think these papers of 2011 are pretty complete. You open them up and you get the answer. In small scales, you should see nothing, because the power spectrum does not couple scales, so you are safe. Yes, and for the spectrum, it's important only at very large scales or for the squeeze limit. Like at least one of the scales has to be large.
No, Rogério, if you use class, you can choose the gauge, you get the power spectrum, and if you choose Newtonian, it's completely different from synchronous in very large scales. It goes up and the synchronous goes down. You can even choose, it's totally crazy like this.
There is someone.
This is also addressed to Jorge. So now that you're computing these relativistic effects, you know, a few of the like Galilean invariance isn't something that you actually have anymore. So these kernels that you have, when you compute things in like regular SPT, they are. Oh, okay. I guess I wasn't paying attention. Great.
Yeah. So you no longer have Galilean invariance. That's true. And indeed, the kernels diverge in the IR. Indeed, they do. I mean, there is no fundamental reason why they shouldn't. And we didn't do it. Maybe it's something we should do. You could compute them because they are not Galilean invariant, but there is still the equivalent symmetry, something like, quote unquote, the equivalence principle. So there is the generalization. And so you could get we did do it at the level of the kernels. We checked that each kernel satisfied this symmetry. But we didn't check what it implies for the IR loops. However, I think it is physical that there is an IR divergence. The IR cutoff is physical. There is a maximum scale that you can measure. And indeed, modes that are bigger than this scale induce supersample effects on the short scales that people have computed, etc. So I think IR cutoffs are, my personal opinion is that IR cutoffs are physical. Contrary to UV cutoffs. It's not strange if your observable depends on the IR cutoff. I would like to discuss that further, actually. If someone has any opinion on that.
For me, go ahead. If there are no other questions.
But isn't it that the moment you reach your cutoff, which is the Hubble scale, then the argument of diff invariance is going to save you because there will be no observable consequence of these super horizon modes. And
yeah, so if you compute an observable,
yes,
you should not get something that depends on this. For
so
the quantity
the same IR cancellation should be
yeah, but it should I expect it to be much more subtle, right? It should be a cancellation not between loops, but also between different effects. Like this happens for the CMB. There is a cancellation between the second order stuff in the metric and the photon propagation, and this cancellation is different in every gauge.
Yes, because but they come from the same metrics.
Yeah, sure. So I expect that to happen when I compute an actual observable, but we are doing it so. Yes, and we know I expect this to happen because our kernels satisfy the consistency relation, which encodes this physics precisely. So, but the fact that the relativistic consistency relation that I wrote with you is non-zero tells you that the cancellation does not happen at the level of delta.
Sure. Yeah. That's
yes, and that's it. That's all I'm saying. Yeah.
If there are no questions, I think we can close the day here. Thank you all for attending. Let's thank again the speakers and see you later, 7:30 at the Universe. Okay, so 8. If I said 8,